Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to the mean value or average value of AC parameters. So in the previous video we discussed calculating the mean or average value of alternating current and its mathematical derivation. Here we'll do the same for alternating voltage. So the process will be the same, just some minor changes. So a quick review. So we know that alternating voltage and current, the alternating parameters, they vary in terms of magnitude and direction. Magnitude changes with time continuously and direction or polarity it reverses periodically after fixed intervals of time. So the alternating voltage, which can be expressed in this form, the instantaneous value Vt expressed as Vmax sin omega t, where Vmax is the amplitude or maximum value or peak value, omega is the angular frequency, t is the time. Here no initial phase angle is considered, but when we include phase angle, it will be plus minus phi depending upon whether the waveform is leading or lagging. Plus for leading, minus for lagging. This is the general waveform of an AC voltage. Positive half cycle followed by a negative half cycle with no initial phase angle starting from 0. Peak values, positive peak value plus Vmax and negative peak value minus Vmax, total time period T. The time period of half cycle is T by 2. Same can be done for alternating current, because when an alternating voltage is applied to a circuit, it results in the flow of alternating current, where IT is equal to Vt by R. So IT will be equal to same Imax sin omega t with no initial phase angle, IT being the instantaneous value, Imax the maximum, omega is the angular frequency. Here initial phase angle is considered. Now we'll do the same thing here, where the basic process of calculating the mean or average value is to find the average of the waveform. Okay, the problem with such a calculation for symmetrical waveforms is that in symmetrical waveforms, the positive and the negative half cycles, they're equal in magnitude but opposite in direction, because the area of the waveform which is above the time axis, that is considered positive, and which is below the time axis, that is considered negative. So they are equal in magnitude, opposite in direction, so they cancel out each other. So for that, previously we discussed the mid-ordinate method, where we divide the entire, we consider one half cycle, which is basically the positive half cycle, and we divide it into equal parts of equal time durations. The width on the time axis of each part, that is equal. Then for each part we find out the middle portion, which splits the time axis in two equal parts. Okay, the middle portion of each part, which is called as the mid-ordinate values. Here I1, I2 and I3, which are marked by these red dotted lines, they are the mid-ordinate values. Okay, so now the average or mean value is simply the sum of these mid-ordinate values divided by the number of mid-ordinates. Okay, for current, I average or I mean, that is equal to I1 plus I2 plus I3 plus In by N. For voltage waveform, it is the same, V1 plus V2 plus V3 plus Vn by N, where I1, I2, I3, N are the current mid-ordinate values, V1, V2, V3, Vn are the voltage mid-ordinate values. So this is the mathematical calculation part. Now the mean or average value determination, it signifies an equivalent DC representation of the AC waveform. Okay, suppose we consider any AC current waveform or AC voltage waveform. Now what will be its equivalent DC representation? That we are trying to find out. So here the definition says the same definition as we considered it for the alternating current, but here instead of current it will be voltage. So the half cycle mean or average value, why we are using half cycle? Because if we consider the total cycle, the average value will become 0. So the half cycle mean or average value of an alternating voltage is that value of steady voltage. Here we are trying to find out an equivalent DC voltage which exactly represents that alternating voltage. Okay, so is that value of steady voltage or DC voltage which would send the same amount of charge through a circuit for half the time period. Okay, half cycle, half the time period, that is T by 2, as is sent by the alternating voltage through the same circuit in the same time. So that is given by V mean or Vm or V average, which is equal to 2 by pi V max, which is equal to 0.637 V max. So what we are trying to do is, suppose we have an alternating voltage waveform and we consider this positive half cycle of duration T by 2. So suppose this positive half cycle, this portion of the alternating voltage is applied to a circuit. Okay, it is applied to a circuit. Then it will send the same amount of charge resulting in the form of flow of current. It will send the same amount of charge as is done by this DC voltage, which we are calling as mean or average voltage, V mean or V average. Okay, so it will send the same amount of charge as is sent by this DC voltage for the same time period. Time period was the same, T by 2. So the positive half cycle of this alternating voltage is the same as this DC voltage, which is equal to 2 by pi V max or 0.637 V max. So this is the equivalent DC representation of this positive half cycle of this AC voltage waveform, only the positive half cycle. So this positive half cycle voltage is the same as this DC voltage. So applying this AC voltage for half the time period for a duration of T by 2 will transfer the same amount of charge as applying this DC voltage for the same time period, that is T by 2 seconds. Okay, this is the equivalent DC representation of this AC waveform, the positive half cycle AC waveform. We are not considering the negative half cycle, we are not considering the total cycle, because if we consider the total cycle, the average value will numerically it will turn out to be 0, because the positive and the negative areas, they will cancel out each other. So for that we consider only the one of the half cycles, preferably the positive half cycle. Okay, so here we got this value. Similarly, we got for the alternating current, I mean Im is equal to 2 by pi I max, which is equal to 0.637 I max. We mathematically derived it also. Here also we'll do the same, we'll try to derive it mathematically. So for now you just understand that this value is the equivalent DC value of this positive value or positive half cycle of the alternating current. DC representation of the positive half cycle AC waveform. Okay. So now we'll try to mathematically derive the mean value or average value of the alternating voltage. So let us say we have a circuit, okay, where we have an alternating voltage. Okay, VT. So when this alternating voltage is applied to this circuit involving a resistor, it results in the flow of an alternating current. Okay, the direction of the current reverses periodically. During the positive half cycle it is like this, during the negative half cycle it is opposite, clockwise then anti-clockwise. So here let this time varying alternating voltage instantaneous value, it is given by Vmax sine omega t. Okay, so we can represent it as this. Okay, this plus Vmax minus Vmax 0, this is t by 2, this is t. Okay, this is the instantaneous voltage. Now the current will be equal to Vt by R, which will be equal to Vmax by R sine omega t. This is the current, okay, the time varying current. This is the instantaneous current. Now since the calculation of mean value or our average value, it is related to charge transferred during the positive half cycle, okay, the positive half cycle of the alternating voltage from time instant 0 to t by 2, half the total time period. Then we have to consider this current, because charge is transferred due to the flow of current, okay, rate of flow of charge is equal to current. So here if we consider this expression, okay, I'm highlighting it, this one, IT is equal to Vmax by R sine omega t. We are representing the time varying current in terms of the maximum value of voltage. So this is the expression. So let IT be constant for a certain period of time, okay, as we did for this alternating current. So let IT is equal to Vmax by R sine omega t remain constant for a duration of dt, small duration dt. Then the small amount of charge dq which is transferred during that time duration, it will be equal to it dt. Why? Because current is equal to rate of flow of charge, that implies q is equal to it. So small amount of charge transferred in duration dt is equal to it dt. Now that implies the total charge transferred during the positive half cycle of the alternating voltage q is equal to integration of dq from 0 to q, then we integrate it dt from 0 to t by 2, because we are only considering the positive half cycle of the alternating voltage. The positive half cycle of the alternating voltage means the positive half cycle of the alternating current also. So here we'll replace it with the original expression, which is equal to integration of 0 to t by 2 Vmax by R sine omega t. Okay, this. So that means that is equal to Vmax by R 0 to t by 2 sine omega t. This is sin omega t dt. Okay, here dt. Okay, so now we'll integrate sin omega t dt, which is equal to V max by R minus cos omega t by omega. So we'll write this omega here, V max by omega R cos omega t minus cos omega t from t by 2 to 0. Okay, no problem here. Then we'll take this minus outside. Okay, integration of minus sin omega t, it is because here we are integrating it with respect to t, so omega behaves as a constant. That's why we took it to the denominator omega, and sin is minus cos, integration of sin is minus cos, lower limit 0, upper limit t by 2. So that is equal to minus V max by omega R cos omega t from t by 2 to 0, same as we did for alternating current. Then so it is equal to minus V max by omega R cos omega t by 2 minus cos 0. So here we'll replace omega with 2 pi by t. So we'll write it as V max by omega R cos 2 pi by t. We are writing omega as 2 pi by t, 2 pi f or 2 pi by t into t by 2 minus cos 0. Okay, here we are writing, we replaced omega with 2 pi by t, which is equal to 2 pi f. F is the frequency in hertz, t is the time period in seconds. F is equal to 1 by t, this. So here what will happen, tt will get cancelled, 2 will get cancelled. So here we'll have, that is equal to minus V max by omega R cos pi minus cos 0, which is equal to minus V max by omega R cos pi is minus 1, cos 0 is 1, so minus 1, which is equal to minus V max by omega R into minus 2, which is equal to 2 V max by omega R. So what is 2 V max by omega R? It is the total charge transferred by the positive half cycle of the alternating voltage from time duration 0 to t by 2. This is the charge transferred by the positive half cycle of the alternating voltage from 0 to t by 2, 2 V max by omega R. Now we want to determine the equivalent DC representation, the DC voltage. Okay, so what we are trying to do is this. Here we have the positive half cycle of the alternating voltage. It transferred a charge of Q is equal to 2 V max by omega r. We want to find out its equivalent DC representation. Okay, this is from 0 to T by 2. Suppose we transfer a DC current for the same time duration T by 2 and we call it V mean or V average, that is the DC current. We want to determine the value of this DC current. So by definition, this DC voltage, it will also transfer the same amount of charge. Okay, it will transfer the same amount of charge. So the current, let the DC voltage be V mean. Okay, so the current, the mean value of current, it will be equal to V mean by R. Okay, V mean by R. Now the charge transferred by this current, which is equal to V mean by R in time duration T by 2, that is equal to I mean into T by 2, which is equal to V mean by R into T by 2, because we are applying this voltage to a resistance R. So this is equal to V mean by R into T by 2. This is the charge transferred by this DC voltage, V mean by R into T by 2. By definition, this value, okay, this value and this value 2 V max by omega R, it should be the same. Okay, it should be same because we are trying to find out the equivalent DC representation of this positive half cycle of the alternating voltage waveform. This is the positive half cycle of the alternating voltage waveform. What will be its equivalent DC representation? Suppose we apply this positive half cycle alternating voltage to a circuit, a certain amount of charge is transferred. What is the equivalent DC voltage which we should apply to the same circuit which will transfer the same amount of charge? That we are trying to determine. That value we are trying to determine by this mean value calculation. So means 2 V max by omega R is equal to V mean by R into T by 2. Okay, so that implies, so here we'll replace omega with 2 pi by T. That implies it will become 2 V max by 2 pi by T into R will be equal to V mean T by 2R. That implies 2 V max T by 2 pi R is equal to V mean T by 2R. So here we'll cancel out T, 2, R. That implies V mean is equal to 2 by pi V max, which is equal to 0.637 Vmax. Okay, this is the equivalent DC value of the positive half cycle of the alternating voltage. So this value here, the equivalent DC value, of this positive half cycle of the alternating current, that is equal to that is equal to 2 by pi Vmax, or 0.637 Vmax. This is the equivalent DC value of this positive value of the alternating voltage. This V mean or V average is the equivalent DC representation of this positive half cycle of the alternating voltage. I am repeatedly using positive half cycle because we are only considering one half cycle, the positive half cycle. We are not considering the entire waveform, because then the DC value or the average value, it will become 0, because the positive and negative cycles, which are of equal magnitude and opposite direction, they will cancel out each other. So here we have calculated the value of the mean value or average value, which is equal to 2 by pi Vmax, which is equal to 0.637 Vmax. Okay, here we have mathematically derived it. Okay, so this is the thing.